Hi everybody, we're going to be starting and discussing how to do composite beam design for a steel beam on using the AISC specification. So I wanted to know where the information is located in the specification of AISC. It's going to be chapter I, design a composite member. Within the composite member, there's a lot of information of different types of composite items, but the one that we are focused on are composite beams with a metal deck with shear studs, shear-headed studs, as we discussed before. And so as we go through it, the chapter is I, and let's see, the first thing that you want to do is actually focus on sections I3, flexure, because beam is in flexure. And before we even get started, we want to talk about effective width. And so effective width pretty much means that if you have a beam, and this is a plan view, right? Let's say that there's a girder right here or something. So if we're looking at, say, this beam, for example, and let's say that this is 10 feet, and this is 30 feet. Okay, and if we cut a section through this and look at what it looks like, what you'll see is that you're going to have a beam and the middle deck is going to go sideways, and on top of that you're going to have concrete. Okay, and then the shear studs would be, oh shoot, sticking up a little more. Usually detailing, at least the way I've done it, is about 1 inch from the top right there. Okay, and so that section's right here. Now what effective width is really saying that as our concrete extends outwards, right? Because really you have 10 feet of it from left to right. What they're saying is that how much of it can you actually use to engage in the steel beam? It's similar to shear lag in a sense where you're not going to be able to use the entire width of the concrete at times. So what the code is saying is that you need to follow these three guidelines, right? And it says effective width of concrete slab shall be the sum of the effective widths for each side of the beam, each of which shall not exceed of these. So you, at the end of the day, will take the minimum of those three. So let's look at the first one. 1/8 of the beam span, okay, center support. So center just means that literally from grid line to grid line, right? Because realistically, the beam flanges kind of come in here for that beam. So that the span actually can be possibly a little less, but they're saying center. Keep it simple. Okay, so what is that? 1/8 of the beam span. So you'll take 30 feet divided by 8. Center supports, right? 1/2 the distance to the center line of the adjacent beam. So that's literally talking about halfway, right? So that's going to be 5 feet because it's total 10. And then the distance to the edge of the slab. In this case, the distance to the edge of the slab, it doesn't really apply unless you're at the edge of a building. And in this case, it doesn't really apply. So then what we will be doing is utilizing really the first two. And so when we look at this, I don't know what 30 divided by 8 is. Let's see what it is. It's going to be 3.73. And that's going to be 5 feet. So that's going to be the governing width. Okay. And remember, there's both sides of it. This section talks about the form deck, right? So usually it's the typical product is going to be Verco. Okay. And again, we've had photos of it in other lectures, but this deck that sits on top, that's the formed metal deck, okay, that sits on top of the beam. So there's all these kind of requirements. I'm not going to go through it, but you should be kind of keying in on what the requirements are. For example, you can't have a steel deck. Slab thickness above the steel deck should not be less than 2 inches, right? So they require to have minimum. The concrete side should be connected with steel-headed stud, welded either through the deck, or directly to the steel. Pretty much what happens really is that you burn through the deck, and headed stud is what we refer to as a Nelson stud, and it's usually a 3/4 inch diameter, and it's got so the diameter of this is going to be the 3/4 typically, and this is the head. Okay, and pretty much at the same time, when you're looking at the strength, you're checking for these different sections to see which is going to be the governing for your concrete compression or the crushing and all that. And finally, to find out what the capacity of the headed studs are, you would use this equation down here. Not steel channel. Oh, shoot. Did I miss it? 106. Okay, well, anyways, you'll see that this table right here is going to assist in giving you the shear capacity of the Nelson studs and how to calculate it. I think I missed the getting that section over, but I've had the equation in this example coming up, so not to worry. But let's go through this really quick. If you have no decking, then your RG and RP essentially is fixed. Deck orientation parallel to the steel shape, right? Deck orientation perpendicular, parallel. So understand that if it's a beam or a girder, they have different RG and RP value. In addition to that, the number of steel-headed stud anchors occupying the same deck rib, okay? 1, 2, or 3, okay? So if you have a beam and we're looking at the top side of it, what I'm drawing right now is a web, okay? And this is the flange. Your metal deck, if I'm drawing the low flutes only, because that's where the Nelson studs will be, would be like this. And so what they're saying is that within that deck oriented perpendicular is this case, is that do I have just one Nelson stud, or do I have 1, 2, 3 Nelson studs, right? And you could see, just imagine this, as you get this is not exactly proportional, but if you have an entire pizza and it's just you get the whole entire thing, okay? And so what they do is they give you a reduction. If you're sharing between the two, usually it's like 50-50, right? But because you have more concrete around you, you'll get 85% of it. And then if you have 3 or more, you get 70% of it. That's essentially what it's saying. All right, so this is kind of a RAM output of what we're going to be doing. Just note that in this case, we're doing normal weight concrete. It's 4.5 inches, right? Concrete thick above is 4.5, right? And they've got all these different information, and so we're going to be attempting to go over these things. So, and this is the second page is talking about deflection, all that. Now, here what we're really going for is what we call partial composite. Partial composite means that your shear studs are going to be governing it. And so what's missing over here is the shear stud. That needs to be in there. Okay, and you'll see what I mean. Okay, first thing what you want to do, based on your beam, you're going to select all the properties that you can get out of the AISC table. Okay, here you're going to be choosing your B effective. So your B effective times the thickness of the concrete, and in this case it's 90. Okay, And then your compression from the concrete is going to be 0.85 F prime C, area of the concrete. Okay, and so that comes out to be that value. So the concrete that you're considering is that. Okay, and I've noted right here that for beams, this part of the concrete is ignored since it cannot be compressed based on the flute voids. For girders, the affected concrete at the lower flute can be used. So essentially the difference between a beam and girder is whether you utilize this portion or not. Okay. So now right here, what we've done is taken the concrete, which is based on the B effective. Remember that table that we talked about, what the B effective is? So even though you can have like say 10 feet total, what it's saying is that in this case, based on the span, it was saying that you got 90 inches instead. Okay, so let's kind of verify that really fast. Is that 1/8 the beam span, center to center. 1/8 the beam span is probably what governs. So total is 30. So when we take 30 and 8 divide, we got 3.75. We do 2 times, and then we get 90 inches. Okay. Remember, it's that table we're looking at is for each side of the beam, right? So each it accounted for effective for here and then effective for there, and so that 2 is where some people will get lost and confused and all that stuff. Okay, and it also is referring to, like, let's just say this is your edge of the building. You essentially don't have that concrete, right? So you're just going to be limited to what that table is showing, and that's where you use that C that we ignored. Okay, so we've got the concrete figured out. Now we're going to talk about the compression of the shear stud. So remember that table we're looking for, which is the RG and RP. So based on our configuration, based on our concrete and all that stuff, what we found is that the QN is 17.2. Okay, and so what you do is you take the summation of the QNs, okay, and then you'll get the, in this case, 258. Okay. So what is 258? So let's see how many studs we have. Matching 17.2. Number of studs, max, partial, actual. So it seems like we use 30 studs. Okay. So let's see if that's 17.2. And then QN, yeah, 17.2. 258 is what I get. So what I do is I'll take, to get that value, I'll take 17.2 kips times 30 studs divided by 2, because your shear is essentially divided 2 because it's going different ways. And so your shear resistance is going to be 258. And so the 258 is less than the total concrete and compression. So this would govern your design. Okay. Essentially, if this exceeded or matched this one, then you wouldn't have partial. You would have what we call full composite. That means you're engaging the entire section. Okay. Partial means that as the concrete is being sheared in and out this direction, that you don't have enough studs to grab all the concrete that you want. So you're getting, in this case, and you can see the percentage. For the percentage, you could take a ratio of that to see what it is. Okay. Now, we have to check for where the PNA occurs, which is the plastic neutral axis. Okay, so we have the compression, right? We also know that that since we have BF times TF times, in this case, 50 KSI steel, right? That's equal to 83.7 kips. And you compare that against the concrete and compression. So you know that the PNA is in the flange. The plastic neutral axis is in the flange. Okay, so this is where it gets pretty complicated. So, okay, so we're saying that the PNA happens within that section somewhere, that it happens within that kind of section. So since T max minus TF is less than QN, then PNA is in the flange. Okay, we're saying the same thing. And so when you have the QN plus the compression of the flange, it's got to equal to your T max minus your compression of the flange. Okay. So what that means is that you have 258, which is your QN. You've got the compression of the amount of compression in the flange, and then the T max, which is your 324. Okay, PNA is equal capacity on each side of the playing field. The line that determines equal capacity is your plastic neutral axis. So if we draw that out right here, that part of the flange is in compression in this case. Now, if all that compression was held within the concrete above and it did not engage the steel, then your calculation would be actually a lot easier. Okay. So your PNA then is going to be a little short of that. And remember, you have your concrete, right? So right here we have 2 of F1 equal to 66 kips, and CF is equal to 33. So then when we have the BF of the flange times the D times the FY, we get the 33. So when we're solving for this, we can find out the equilibrium to find out, in this case, what D prime is. And D prime is 0.131. Okay, so the PNA then is going to be the D, which is the total distance from the very actual top, minus the D prime, equal to 13.7 minus 0.131. And it comes out to be 13.57, which matches what the RAM output has if we take a look at it and scroll back up. Okay. Now here's what ends up happening is that this is the equation. If the PNA enters into the web, this essentially makes your life a lot harder. And this will typically occur when you have a girder. Okay. Okay. So to compute the nominal capacity of the beam, Mn, okay, you have the tension at the center if the entire section is in tension. But this is not the case since I guess this is an example if the web is partially in tension. So new centroid for reduced tensions area in the W beam, 14 by 22, but hold on, in this case, since web is partially in tension, this is meant to be flange, okay. So the flange is partially in, I think it's, entire section is in tension. It's not the case since the flange is partially in tension, not fully in tension is really what it's saying. So because you have a little compression right here, what it's saying is that your entire section of the steel is not in tension. And so what we have to do is to find out the new centroid for the reduced tension of the W member. So we have the total area of the beam, the Y bar, right, which is from the center member, I believe it's to the PNA, and then the AY when you multiply the two. Now, the compression of the flange, right, is going to be calculated through right here, which is the amount that it's in compression, the flange width of it, right, and what does that equal to is 0.0655. And so essentially what you're doing is find a centroid based on the reduced area. So as you can see in the diagram right here, you're taking that portion of it off right now. Okay. And then your final Y bar is going to be right here. Okay. Now, in order to calculate the moment capacity of everything, solve the centroid of the concrete compression. You have A is equal to the total shear studs that are in shear divided by 0.85, 3 KSI 90, and that equals to 1.13. So okay. I think what we're saying is that if this was in this area, that would be the case. But in this case, when we're solving for the area of concrete compression, we actually find out that the compression portion of it is 1.13 inches, which is right there. Okay, and so only this portion of the concrete is actually engaging compression from the shear stud. And then we also have the amount of this part that's in compression that is going this way due to the PNA, right? Because the PNA is like right over there. So this is like right around there. Okay, so as you can see right here, you end up just taking some of the moments. So you have the concrete that's up there. You have the flange that's partially in compression, and then what we could do is say that let's say that the blue portion right here, that's in compression, and let's just say that this whole area is in compression, and then the area in red is in tension. Okay, and so once you get this mapped out, you end up taking some of the moments, and so similar to what you learned in statics, you take some of the moments anywhere about any point, but in this case, it's probably the easiest and the best to just take it about the base, because if you measure everything from the base, you just take, force times distance, right? So we want to play that kind of tempo in our head is moment is equal to force times distance, right? So here's your distance, here's your distance, here's your distance. Well, tension's going this way, compression's going this way, compression's going this way. So if we say this is positive, this is negative and negative, or vice versa, it really doesn't matter. At the end of the day, what you find out is that your moment capacity is 333.9 kip foot, and then that matches the amount that RAM gets within less than 1% of error. And obviously, you apply the phi factor on top of that afterwards. Okay? Okay. So now that we've actually solved for the moment capacity for that one, the next challenge is to solve for the moment of inertia. And so the question is, why do we care and why do we need the moment of inertia? Moment of inertia is going to be giving us the what we need to calculate deflection. And so when we have deflection, when we don't have the concrete composite engaged, we would just use actually the bare section. But then once everything is cured and you have the full load, then you would use what we call the entire section or transform section. Okay, so this is going to kind of go through and talk about, a lot of this is going to go back to statics. Okay, or this would be in structural materials. So here, which is a modular ratio, takes into consideration of the steel modulus and the concrete modulus. And per the specification I2, you'll find how you get the concrete. This is WC 1.5 F prime C. And so this is in KSI. The difference between steel and concrete, if you came from a concrete class, typically in the square root, it's always going to be PSI, but for concrete, it is in KSI. That's why the formula looks a little different if you took a concrete course. Okay, so once we do that, we get the modular ratio. And so we knew that the B effective was all the way out here. What the modular ratio does is it shrinks it. And this is now transformed into steel. And so you have this one also into steel. Okay. Let's see. So once you do that, a lot of this is kind of similar from statics, area, Y bar, and all that. And so when you do that, you have the concrete transformed portion of it, finding your centroid and all that. And what you'll find is that you'll get that 17.2 is where essentially your neutral axis is going to be. It's 14 by, so I don't know if it's up there or something. So, and so RAM gets 17.4. It's within our error that we've discussed. I don't know what WTF stands for, but it probably is expressing how the difference between this and this is. Okay, so now that we have that, what we do is we have the parallel axis theorem. This is essentially parallel axis theorem. Parallel axis theorem says moment inertia of the steel member is W14, you'll get from the steel table. The moment inertia of just concrete, and parallel axis theorem, which is AD squared. AD squared. Okay? And you'll find that if it was 100% fully composite, then it will be 1013.48. RAM is getting 1100.62. I think because my Y is off a little, then everything's a little off, but yeah. So finally, how do we get what we call I effective? That's essentially what you're going to be using. Now, you have the I effective, and really the thing is you're going to take this kind of ratio, right? The ratio between your the shear stud and the compression, and when you do that, you take this ratio. Essentially, you'll get what we call the I effective. Okay, and that kind of completes this lecture. So take a look at this. This will also be uploaded, so you can kind of take a look at it and take a deeper dive into understanding what's going on here. So yeah, just do that.